Hello student, welcome to our third lesson where we are going to look at domain theory of magnetism. Now, in this theory, it states that magnets consist of a small magnetic groups that are called magnetic domains. Remember, in Form 1, when we are talking about particulate nature of matter, we found that matter is made up of tiny particles. And these tiny particles are ever in motion. So when we come to a magnet, these tiny particles, we call them subatomic magnets. And those subatomic magnets are contained in groups, what we call the magnetic groups. And those groups are the ones that we are calling magnetic domains. Now, domains have a common magnetic axis, and domains comprises of smaller subatomic magnets, or what we call molecular magnets, called dipoles. Now, the dipoles in a particular domain point towards a common direction, giving the domain an overall north pole and a south pole. Now, the total field outside the magnetic material is the sum of the individual domain field. Now, in a unmagnetized condition, the dipoles in neighboring domain arrange themselves in closed loops. Therefore, the domains, however, align in different directions, giving no resultant field outside the material. Remember, we are talking of unmagnetized material. Although in a particular domain, the dipoles are facing in one direction, when you combine them, you find that the dipoles of a given domain, the magnetic field of a given domain will cancel, and the resultant end of the result of an unmagnetized material is that the magnetic field is zero, as shown in this diagram. Now, this group that is covered here is what we call the domain. Now, these small magnets that are inside are the ones that we are calling the dipole. Now, in this domain, all the dipoles are facing north, upwards. So it means that now this edge is of this domain is north and this edge is south. When you come to this second domain, this part, you'll find that they are pointing towards that direction. So again, this edge will be north and this edge is south. That is why now we are saying the domain, because of this dipole, it means that each domain will have a north pole and a south pole. And now the overall, this is unmagnetized material, the overall magnetic field will be zero because the field of each domain will cancel out, and you'll find that this material that is unmagnetized will have no magnetic field. Then from there, during magnetization, the dipoles align to face one direction. In other words, this is facing upward, this one towards that direction. When you are magnetizing or when you are making a magnet, these dipoles will tend to look, or they will align so that now they face in one direction. But during demagnetization, that is the destruction of a magnet, the dipoles in a magnet are disturbed and disarranged, then they settle back in their preferred direction, that is in their different direction, and therefore we say that the magnetism is lost. Now, the magnetic saturation is attained when all the dipoles are fully aligned in one direction. The magnet can then be said that you cannot magnetize any further because all the dipoles are facing in one direction, as shown in our diagram here. You have, these are the domains with different dipoles in each domain facing different direction. This is unmagnetized material. Now, when you put this in a magnetizing field, the dipoles align such that they face in one direction. And when all the dipoles are facing in one direction, then we say that that material has attained what we call magnetic saturation. That is, when all the dipoles align themselves in one direction, the material is said to be magnetically saturated. And therefore, no further magnetization can take place beyond this point. Now, when the magnetizing field is removed, the domains of hard magnetic material. When we talk of hard magnetic material, these are materials that are very difficult to magnetize. And when we are saying that the magnetizing field is removed, the domains of hard magnetic material maintain their new orientation. In other words, hard magnetic material will retain its magnetism even when the magnetizing field is removed. But when you are using a soft magnetic material, this soft magnetic material, we say that they are easy to magnetize. And when you magnetize them, they lose their magnetism after a short time. So it implies that when the magnetizing field is removed, these soft magnetic material have their domains returning to their original arrangement, and therefore they lose their magnetism. Then from there, we move to magnetization and demagnetization. We start with magnetization. Now, magnetization is a process of making a magnet from a magnetic material. Remember, a magnetic material has domains, has dipoles that are facing in different directions. So we can only make a magnet from a magnetic material. Now, during this process of making a magnet, dipoles get aligned. And in a partially magnetized material, most but not all domains are aligned in one direction. But when a material is fully magnetized, all the domains are aligned in one direction. And at that point, we say that that material is magnetically saturated. There are 4 common methods that are used to make a magnet. 1, we have induction, stroking, hammering in north-south direction, and electrical method using direct current. Then we start with the first one, induction. Now, this is a method where a magnet induces magnetism in a magnetic material in contact with it. In other words, you just bring a magnetic material closer to a permanent magnet. So the end of a material that is in contact with the magnet attains a polarity opposite to the pole of the magnetizing magnet. In other words, if you bring a magnetic material closer to a north pole, then that end will become a south pole. When we talk of polarity, we are talking about the poles of that material as shown in this diagram. We have a permanent bar magnet, then we have steel pins. These steel pins are magnetic materials. So when you bring it closer to north pole, the end that is closer to this, the end of a magnetizing material, then becomes opposite, or it attains a polarity that is opposite. So if this is north, then this one becomes south. And now, because now this one has become a magnet, again it will attract another pin. So again, this was south, north, then this end becomes south. And the process can continue to, you will have a chain of iron filing, steel pins attracting one another. So when you have 2 pins that are attached on one end, you'll find that there will be repulsion, because this end will attain a north and a north, this end will attain a south and a south. So these 2 ends will have like poles, and we know that like poles repel. Now when you bring closer another magnet, that is permanent bar magnet, closer to this one, you will find that the repulsion will be increased, because if this is south, this is north, this is south, this is south, and then you are bringing another south, that is, all these are like poles, so there will be a greater repulsion. Then from there, we move to the second method, where we have stroking method. Now in this method, a magnetic material that is being magnetized is rubbed repeatedly, or we say that it is stroked repeatedly using one end of a strong magnet. Now the stroking, or as you rub, you align the domains, and therefore magnetic material becomes a magnet. We have 2 types of stroking. One, we have single stroke and double stroke. So we start with the single stroke. In this method, the magnetic material is rubbed or stroked with one pole of the magnet from one end to another, lifting it away as shown in this diagram, this one. So you move from one end, we are starting from end A, moving, we stroke, we rub, then you lift, then you ensure that you are using the one pole. Again you move, you lift again, you do it repeatedly several times, and at the end you are going to find that this one, this steel needle AB will be magnetized, because as you stroke, the dipoles in the domain are aligned. Now the head of the magnet, or the head of magnetic material, where the magnet finishes, the head that is finishing, stroking, acquires an opposite polarity to that of the stroking magnet. So in our case, since the stroking head is north pole, then head B acquires south pole. This is where now this one is finishing. So it will acquire an opposite of this. So north you get south pole, and this head will automatically become a north pole. Then from there, we move to disadvantages of a single stroke. The disadvantage that we have is that the magnet that is formed is having one pole that is nearer the head of the magnetized material than the other. So in other words, we are saying that the pole is nearer one head than the other. This disadvantage can be avoided by using a double stroke method. So we move to double stroke. In this case, we are going to use two permanent bar magnet, and then we stroke using the two permanent bar magnet. You move this one towards the head, and you move this other one towards the head. Remember, all this head will have the finishing head. And now the disadvantage where we are saying that one pole is nearer the head than the other, you'll find that it is now avoided when we use the double stroke, because we are starting at the middle and moving towards the head. So you have the two diagrams. Here we are using the north pole, south pole. Here we are using the south pole. I mean the north pole and north pole. So as the finishing head will acquire an opposite, then it implies that this one will acquire south pole, and this is south, so this will acquire a north pole. But in this case, again, this is a north pole, so this will acquire a south pole. Again, this one is north pole, then you have that it will acquire a south pole. So you'll have two north pole at the middle that we call consequent poles. Then from there, we move to hammering method, or what we call the mechanical method. Now, when you are using this method, we try to use the Earth's magnetic field. So we make sure that the material that is being magnetized is placed in north-south direction. We place it in this form or in this direction so that we can utilize the magnetic field. So that now the dipoles will try to align according to the Earth's magnetic field. So the head pointing northward will become a north pole, and the one that is pointing southward, or the geographical south, will become a south pole. This is what we have here. You are placing it in north-south direction, and then you hammer. As you hammer, you are disturbing the dipoles, and because there is Earth's magnetic field, that magnetic field will allow those dipoles to settle in north-south direction. That way, you are able to make a magnet using a mechanical method. Then the angle theta here, we call it the angle of dip. Then we have the fourth one, electrical method. In this case, you are supposed to note that we are using a direct current. A direct current means that it is coming from one direction or one terminal towards the other. So it will always point, or the current will always come from the positive terminal towards the negative terminal. Now the magnetic material to be magnetized is placed inside the solenoid, and that solenoid is then connected to the battery. Then the switch is closed and the current will pass through the solenoid for some time, as shown in this diagram. So this is our circuit here. This is the positive terminal, and this is the negative terminal. This is our solenoid. So the material to be magnetized is placed inside, and then you just switch on. This is ammeter. It's just showing whether there is current that is flowing, and this is rheostat, and this is to vary the amount of current that is passing. If you want to increase the current, if you want to reduce the current, and then you can be able to see the effect of reducing and increasing, we use the rheostat or a variable resistor. Now, when you allow it to pass, that current, because it is coming from one direction towards the other, then the dipoles will be forced to, or they are aligned towards one direction. And that way, after some time, you'll find that this material will be magnetized. Now, we need to know how to get the polarity of this material. And to get the polarity, we use two rules. Remember, the polarity depends on the direction of current. So we use what we call the right-hand grip rule that will help us to identify the poles of that magnetic material. The right-hand grip rule states that if the coil carrying a current is grasped in the right hand such that the four fingers point in the direction of current in the coil, then the thumb points in the direction of north pole, as shown in this diagram. The four fingers are pointing in the direction of current. Remember, we are grasping the solenoid. Make sure that the four fingers are pointing the direction of the current. Then the thumb will point the direction of the north pole. So that way you are able to identify the poles of that magnetized material. Now the pole A in our case here and B can be identified also using the Crook rule. And the Crook rule states that on viewing one end of a bar magnet, the current flows in clockwise direction. If you find that the current flows in the clockwise direction, then that end is a south pole. And if anti-clockwise, then that end is north pole. Remember, you are viewing from one end. So you are placing your eye on this end, and you can see that when you view on this side, the current will be flowing towards this direction, anti-clockwise. So if it is anti-clockwise, then that end becomes the north pole. When you come and place your eye on this other end, you'll find that now the current will be flowing towards the other direction. That is clockwise. If you find that it is clockwise, then that end becomes a south pole. So that is what we call the Crook rule. So we have two rules, right-hand grip rule and Crook rule. And these ones are going to help you to identify the poles of a magnetized material. Then from there we have the assignment. Again, the assignment is testing what we have just learned. So make sure that you revise and then you come and attempt the assignment. So thank you, and let us meet in our next lesson.